Square root of 5 by square root of 5. Okay, it works. For 3, it is a little bit difficult. For 2, it is also obvious because we will obtain 1. For 3, we should obtain 2. Have time? Yes, 6 minutes yet. Okay, let's try for n equals to 3. Is it visible on that blackboard, whiteboard, something? Is it visible?
Not clear.
Yeah?
Yes, sir. Yes, yes, yes.
Not clear, sir.
Yes? Yes. So let's try for n equals to 3. So we have something like this. Of course, it should be 2, yes, because this is F0, F1, F2, F3. We have 1 divided by square root of 5, and here 1 plus square root of 5 to the power of 3 divided by 2 minus 1 minus square root of 5 to the power of 3 divided by 2. Okay, and now we need an equation for making a power of 3 from adding two numbers. The equation is a plus b to the power of 3 is a to 3 plus 3a squared b plus 3ab squared plus b to the power of 3. You remember such an equation from, I don't know, elementary school? Or should I prove it?
Remember, sir.
Yes, thanks. Okay, so now we can use it. So we have 1 divided by square root of 5 because it was. And now 1 to the power of 3 is 1 plus 3 times a squared, so this will be 1 plus b is square root of 5 plus 3a, this is 1, b squared, so this is just times 5, and plus square root of 5 to the power of 3. Unfortunately, it is not possible to shorten, divided by 2. Minus the second element. If we have a minus b here, the only difference is making the power of 3 in some elements. So here b is minus b in a sense, yes? We can just plus minus b. So this will be a to 3 plus, minus 3a squared b plus 3ab squared, because this is square and this erases minus, and minus b to 3. Okay, so in such a case, we have 1 minus 3 square root of 5 plus 3 times 5 and minus square root of 5 to the power of 3. This is the same denominator, which means 2. So finally, we can erase this one, yes, because this is 1 minus 1. Also, this is this one with this one. Yes. Okay. Okay, so finally, we have something like this. 1 divided by square root of 5. And here, this is 2 times, but divided by 2, it is just 3 times square root of 5. And here we have, this is minus, so this is plus. Probably okay. This is minus, minus, this is plus 2 times. So also we have square root of 5 to the power of 3. Something is not good. This is square root of 5, so this is 25. No, this is not square root of 5. Something is not okay.
Sir, I think it's not 3 under root 5.
Where?
And the last step, it's 6 under root 5.
Where?
And this one, 3 under root 5, and below plus 3 under root 5, it's 6 under root 5 on the last step, last.
This one?
Yes.
But this is divided by 2. Yeah, yes. If you write it like this will be 2 times this one divided by 2, and also this will be 2 times this one. Yeah, in such a sense. But still, this is too much. Plus something is not good. Maybe I'll just write it in the too short form. So I think so. Once again, something is not okay. Initial conditions work, so it should be nice. Just a second. I just check for a moment the Fibonacci general form, because I'm not sure if it is okay, but I think so. Where is it? Yeah. Plus, minus, okay. So it should be okay, because this is exactly the same. Yes, sorry. This is the whole. 2 is also to the power of n. Yeah, sorry. So I know just one. Sorry, this is like this. Because all these elements are to the power of n. So now it's okay, because this is divided by what? By 8, yeah? Something like this. Now it's okay. So we can shorten this one. And this 3 makes 2. So finally we have 5 here. So we have 6 plus 2 times 5, because square root of 5 to square, divided by 8, and it is 2. It's okay. Sorry for disturbance, but as you can see, it is just online. Yeah? We are on the red light bulb. Okay, so let us make a short break for tea or something, something stronger, and the rest will be after the break. So 15 minutes break. Okay, we'll end the break in a moment. Just a second. Okay, we can start again. Let us make another example of using this approach with two different solutions. Let it be an example just next. So let us have something like this. A0 is A1 is 3, and AN is AN minus 1 plus 2 times AN minus 2. Okay. So we have something like this. 3 and 3 on the beginning. And next, this is the sum that we take the previous one times 2 and just the previous. So this will be 6 plus 3 is 9. Here we have 2 times 3, this is 6, plus 9, 15. 18 plus 15, what is 18 plus 15? 33, and so on. So such a sequence. So A and B here are A is 1, B is 2, like here, yeah. So we have such a characteristic equation. That x squared minus a times x, so a is 1, a is so just x, minus b, so this is 2, is 0. Okay, so delta is b squared, this is 1, minus 4ac, so this is minus 4, a is 1, c is minus 2, so this is finally 9. Okay, square root of 9 is just a natural number. So we have x1 is minus b, so this is 1, minus square root of delta by 2, so this is minus 1, because this is 3, 1 minus 3 is minus 2, by 2 is minus 1, and x2 is 1 plus square root of delta, so this is 3, so this is 2. That is the general form of the nth element is given by such a formula. As is a times x1, so this will be minus 1 to the power of n plus b times x2 to the power of n. And what about initial conditions? Initial conditions. So how to have the a and b? So we have in this sequence a times minus 1 to the power of 0 plus b times 2 to the power of 0 should be n is a is 0, so this is 3. And the second a times minus 1 to the power of 1 plus b times 2 to the power of 1 should be also 3. Because this is a0 and this is a1. So we have this is 1. This is also 1. So a plus b should be 3. And from here, we have 2 times b minus a, and this should be order 3. This is quite easy. Maybe I will write it in such a form: minus a plus 2b. So if we add these two equations, we'll obtain that here is a and minus a. So we finally have 3b, b plus 2b is 6. So b is 2. And substituting this here, we'll obtain that a should be 1. So finally, we have such a form of the general element of this sequence, that an will be a, this is 1, times minus 1 to the power of n, plus b, which is 2, times 2 to the power of n. Let us check maybe for that one. So this is second interval, so this is a0, this is a1, this is a2. So for the second one, we have minus 1 to the power of n, so to the power of 2 is 1. And here we have just 8, because this is 2 to the power of 3. So 9, okay. Maybe one more, the third one. This is a3. So for n equals to 3, we have a3 equals to minus 1 to the power of 3, which is minus 1, plus 2 to the power of 4. So finally we have 15, because this is 16 minus 1. Is it clear how it works? Question mark?
Yes, sir.
Oh, thanks. Okay, so that's all in the topic of recurrential equations. Of course, we just touch the topic because it is much more complicated, and if we have more complex formulations of the recurrential equations, this is not enough to have just such a simple linear approaches. However, the method of characteristic equation, in sense of substituting and supposing that the general form of the nth element is in the form of something times something to the power of n, is a quite universal approach to some recurrential formulations, because in fact inside the recurrence we have inside this making the power of n, because the next one has the whole history of this submitting inside. If we write here, for instance, that an, this is an minus 1 plus 2 times an minus 2, and if we remember the previous lecture, we have the possibility of substituting, obtaining that this one, this is n minus 2 plus 2 n minus 3, yeah? And the same here, we have that this one, it is 2 times n minus 3 plus 2 n minus 4, which is in fact this is n minus 2, plus this one is 2 times and this one is 2 times, so this is 2 squared times n minus 3, and this times this gives us 2 to the power of 3 times n minus 4, and so on. Yeah. So we have the possibility of finding out the general form of the equation in sense of making such a operations, because as you can observe, in fact, the general form of here is something like this, that this is 2 to the power of n plus 1 plus or minus 1. Yes, in sense that sometimes we add 1 and sometimes we subtract 1. So in fact, this is somehow easy to find out, just guess the result. And for most instances of the recurrential equations, we just write the elements of the sequence, finding how this appears. So we can observe that this is, for example, that this is 8 plus 1, yeah, and this is 16 minus 1. This is 32 plus 1. The next one should be probably 64 minus 1, because this is plus, plus, minus, minus, and so on. So by such a simple observations, we can find out the general form just by guessing the equation. Is it clear? It is somehow general observations that in combinatorics and discrete mathematics, most results are just finding out by observations, because in great numbers world, as for instance real numbers or complex number set of or some sequences, infinities, and so on, we have so-called great numbers laws, in sense that some statements which are true for great numbers. In here we have just combinatorics, so mostly it is based on some tricks and some clever observations to obtain the final result. Okay, the next topic will be relations. Have you any questions to this part of the lecture?
No, sir.
Thank you. So the next topic will be relations, and this is very close connected to the subject of graphs. The next big part of the lecture will be connected with graph theory, but the introduction to graph is connected with relations. And today I will introduce the method of relations and of being in relation, belonging to relation, and this is a kind of it is a little bit different and a little bit similar to functional approach, in the sense that function gives us a relation in which we have the variable and the result of the function. For relation, we can have several values of, it says, the function, but this is not a function, because as we know, a function is just one result. There is no possibility that we have the function in some sense that for some value we have several values possible. This is not a function. Function is that we have one value. In relation, we can have such a possibility that for one x we have the relation with many elements relation. This is function. So in function, this one or this one are not possible, because we have only one value. So we can think about it that a function is a special relation in such a relation that we have only one element being in relation with the variable. Here we can have many possibilities. So this is not the same, but we can think about it that it belongs in some sense to the function is a kind of relation. Okay, relations. We'll think about relation as a binary relation, but the main base of this theory is the so-called Cartesian product. Let it be S times T. What does it matter? If we have a set S, let it be A, B, C, and set T, D, E. So the set of Cartesian product is a set of pairs. So we have AD, BD, we have CD, we have next AE, BE, and CE. So somehow this is quite easy, because this is the definition is like this, that this is a pair of elements, a set of pairs, such that X belongs to S and Y belongs to T. The size of such a set, because this is also the set, is the size of S times the size of T. So if we have here three elements, and here we have two elements, so the size of S times T is 3 times 2, this is 6, as you can see. Okay, so we say that something is in the relation when it belongs to the set of such a Cartesian product. So the definition of the relation. We say that X is in the relation R. That is the same that is in the relation, maybe R with Y. This is the same that X, Y belongs to the set of relation. Because this is pair, of course, R should be the set of pairs. Very easy example. We usually use the relation of being smaller. So we write that X is smaller than 5. That means that the pair 3, 5 belongs to the set which we can write in such a way. This is the symbol of the set. We can write it in such a way. 3 is in relation R in 5. That means 3, 5 belongs to relation R. This is the same. So we use the relations like smaller or equal, being the subset or subset of equal, and very many, belonging, and so on. Yes, so there is very many symbols we can write to show even such a symbol. Yes, which means that is much greater. Maybe I will write it in better form. Yes, this is also the relation, which means we use it from very beginning of our learning of mathematics. But in fact, we use relations, but without imagining that this is belonging to the set. So this is a definition. And maybe I will show another example, a little bit more, maybe not complicated example. Let us imagine that we have a set S like this, This is 1 to 3. And the set T, this is AB. So the set of pairs will be like this. All the elements of pairs with 1 on the beginning. So we have 1A, we have 1B. Yeah, just a moment. Sorry, we have the new room just after the some building operations. So we have S times T. 1 on the beginning, yes. Now 2 on the beginning, 2A, 2B. 3 on the beginning, 3A, 3B. Yeah, that's all. And now the relation. Let it be something like this. This shouldn't be the whole set, of course. This is just a subset of this. So this it can be, for instance, something like this: 1A, 1B, 2A, and 3B. So of course, R is a subset of S times T. This is an assumption. But if we just write it on the diagram, we obtain something like this. We have elements 1, 2, 3 from the set S, and AB from T. And finally, we have something like this: 1 to A, 1 to B, 2 to A, and 3 to B. So this is diagram of being in this relation. Of course, we draw here a graph, but we don't use up to the preliminary introduction the term of graph. This is just a graphical representation. But of course, this is very natural to have the arcs and nodes to show the being in the relation. Some properties of the relation, maybe not properties, but just nice properties of some relations, maybe like something like this: properties of some relations. So a relation can be reflexive. Reflexive relation means that for all the elements of the set let it be maybe something like this. Maybe I will write versus the intro. Sorry. Let the relation R will be a part of the Cartesian product of the times S times S, the same set. So this is relation on the set S. Denote the relation R on the set S. This relation can be reflexive. What does it mean? Reflexive means that for all elements of the S, the pair S XX belongs to relation. So the element is in the relation with themselves. For instance, such a relation is being smaller or equal. This is reflexive because 5 is in the relation with 5. Irreflexive means that for all elements of the S, the pair XX doesn't belong to relation, and the example, maybe here example is being smaller or equal. Yeah? For example, here we have being smaller. 5 is not smaller than 5, so this is irreflexive relation. Symmetric one. Symmetric means that if we take two elements of the set S, X and Y, if X, Y belongs to relation, that we have that YX also belongs to relation. This is symmetric relation. For example, the relation being equal is symmetric. If X equals to Y, so Y equals to X. In sense of being equal, because sometimes this notation is not so obvious. For instance, if you know something about computational complexity, we have something like notation being big O notation. So if something equals to another in sense of being big O, mam wykład, zaraz skończę. No, dobra, dzięki. No. So if we have that big O from n to the power of 3 plus 5 equals to big O from n is maybe like this. Let it be like this, that n square is big O from n to the power of 3. Yes, and n is also big O from n to the power of 3, but this is not the same. So in sense something like this. So this notation to the numbers is symmetric, but sometimes like notation in the sense of being in the class of complexity, it is not. Antisymmetric. Antisymmetric relation is that for all X, Y belonging to S, if we have that X, Y belongs to relation, we have that maybe I will write it in such a sense that and yx also belongs to relation, that means that we have that x equal to y. So this is the only case in which both xy and yx belongs to the relation. And finally, the relation can be transitive. Transitive relation means that if we have three elements, x, y, z, belonging to the set, and if we have that x, y belongs to relation and thank you very much, and y, z belongs to relation, that means x, z belongs to relation. For instance, such an example of such a big relation is being smaller. If 3 is smaller than 5 and 5 is smaller than 10, so 3 is smaller than 10. This is symmetric. Which one is antisymmetric? For instance, here antisymmetric is being smaller or equal. If 3 is smaller or equal, no, maybe in other words, if we have that x is smaller than y and 1 and y is smaller or equal to x, so from this fact we have that x should be y, because this is the only case in which both x and y are in relation with each other. Is it clear, these definitions?
Yes, sir.
I hope.
Yes, sir.
Okay, so graphically, of course, we can write this in sense of some vertices and edges and some arcs, but in fact, these properties, in sense of drawing in the paper, on the blackboard, is very powerful tool. For instance, if we have transitive relation, this is the strong base of something we call transitive closure of the graph. And if late 50s of the previous century, famous algorithms for transitive closure and next for the shortest path are, as we know today, like Dijkstra algorithm, the Bellman-Ford prima Dijkstra. This is based on the properties of the relations and applying them to the computer, which means matrix, in fact, and representation of the relation. Of course, this set of pairs as a set on which a relation works is very natural as in implementation as a matrix. So we have the set of pairs. So in fact, we have 1, 1, 2, 3, and so on. So we can write it in the binary form in sense that we have, let it be the set S. We can always enumerate it. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yes, and here we have some ones, zeros, and in such a method we can remember in the computer if something belongs to relation or no. And so this is very natural for making it in the form of binary matrix. And in fact, the previous first implementations of the famous computer algorithms, as for instance Ford algorithm for transitive closure, or next Bellman-Ford for finding the shortest path, this is based on the representation of the transitive closure and calculating it, because it is very natural that if we have something in the relation, maybe let us try it to the easy example. We have elements 1, 2, 3 here and A, B here, and let us imagine that A is in the relation. A is in the relation with 1. Yeah, so we write here, and 1 is I maybe like this. Let it be 1 to 3 and 1 to 3. So if we have that 1 is the relation with 2, and 2 is the relation in 3, so we can write that 1 is in the relation with 3. This is transitive closure. So this is quite easy to find out what is the result of multiplying of such a property. That something is in the relation with something, and next up to the end of the sequence. Then we just consider here finite sets. So this is quite easy to make an iteration up to the end of the set because the size is finite. But for infinite sets, it is very similar, but for the computer, this is harder. Okay, so let it be a kind of introduction to the relations. On the next lecture, I will show how to formulate it in the language of the graph theory. And next, we'll go to the graph properties and graph algorithms. Have you any questions to remarks to this lecture?
No, sir.
Okay.
No, sir. Thank you so much.
So
Nice
thank you very much. Yes. Okay. And see you next Tuesday. Thank you very much. Goodbye.
Have a good week.